Starting my video. Good morning, madam.
Good morning. Very happy to see you.
Thank you so much, madam.
I am starting the session.
Yeah.
Adi, are you there?
Yes, ma'am, I'm here.
Good morning, attendant. I welcome you all to the third day of SPS Summer School program on IoT on Biomedical and Healthcare Applications. We have 3 tracks lined up for you today and dazzling music performance by Crescendo, the music club of ENR VJAT. We hope you will learn and enjoy the talks and performance just like last 2 days. And we are having 2 live demonstration of our projects. That is live demonstration from 6:30 p.m. to 8:30 p.m. That is one prosthetic hand on voice based commands by Manu Satyasai, CEO Soulboards Technologies Private Limited, during 6:30 p.m. to 7 p.m. And second demonstration, digital health advisory system for chronic respiratory diseases by Mr. SVN Narayana sir, co-founder and director, Solid Seek Technologies, during 7 p.m. to 7:30 p.m. And various IoT boards by Mr. D. Ramesh Reddy, Assistant Professor, VNR VJIT, from 7:30 to 8:30 p.m. I request all the students as well as faculty members who are attending this program, please attend and so learn all these things so that you can teach the same thing to your students. So please don't miss that live demonstration of the project using the same WebEx link. So I don't want to take much time of Vamshis. So Sadia, please start the session.
Thank you, ma'am. Welcome, sir. So our first talk is on fog computing and edge cloud for healthcare by Mr. K. Vamshi. Mr. Vamshi has done his bachelor's in ECE and graduated in 2013. Right after his graduation, he started working to realize his idea of Syntizen, a startup which works with other startups, middle market businesses, state governments, and other corporate companies in developing innovative solutions that make an impact. Co-founded by Mr. Vamshi in 2014, Syntizen is a startup India registered startup incubated at T-Hub, which is India's biggest government-backed startup incubator. Really happy to have you here, sir. Please get started.
Thank you so much. That's a great intro. So can I get the sharing permissions to share my screen?
Yes, sir, you have the presenter access now.
Yeah, 1 second. It's asking my system preferences. Oh. I think it's asking for me a restart. 1 second. I'll just rejoin.
Sure, sir. Ma'am, Vamshi sir is here. Can you please make him the panelist? Yes, ma'am. And also presenter access. So you're on mute. So
Yeah, is my screen visible?
yes, sir.
Great. So I just want to take a couple of minutes to discuss about fog computing and edge computing and edge clouds, and I would like to focus much on healthcare as well. So as a start, I'll just give you a brief about what are the topics that I'm going to cover for the day. So first thing is, what is this cloud environment, and then what are the limitations of the cloud, and then about IoT, about edge computing and fog computing, then features of fog computing, and then we are just giving a comparison between fog and the cloud and how this entire fog works. And then what are the roles and responsibilities of a fog and a cloud in any systems environment. And then we are moving on to healthcare challenges, issues, and then what are the requirements and the vision of how we are going to use fog in healthcare and its applications with and without fog, a decent comparison. And that's how I have planned actually. So when it comes to the cloud computing, it's all about centralizing the entire information into one place. So imagine there are tons and tons of mobiles that we are data is getting accumulated into a cloud environment where the entire information is centralized. So, but what are the limitations of it is basically uh, mainly the connectivity issue. When we have a very low bandwidth or when there is no connectivity, we are disconnected from everything. I mean, we can't actually rely on direct cloud environment when there is no connectivity. And the bandwidth issue, how much of bandwidth we are covering up while we are consuming any kind of application. And the analytics, the entire analytics in a cloud platform is centralized. So some devices has to wait for the response of the cloud till we get a response. The devices are not so actionable. And there are some security concerns as well because most of the PII data is also moving onto the cloud, which may not be needed. And when it comes to the Internet of Things, there are many physical devices, any physical device which has a couple of sensors, a couple of computing in it, as all an IoT device, which is connected to a central environment. So what is this edge computing? So edge computing is basically is we are bringing the processing capabilities very nearer to the IoT devices so that it will be much faster and much accessible and even in the low latencies we can get our things done. So it's basically a middleware between a cloud as well as a end device. And this middleware is we are just moving on to as nearer as possible. So along with this, I'll just go with some real time examples in between so that you'll understand what we are talking about. So as a start, let me tell you about let's say CC camera surveillance. So let us say there are cameras around, and all of these cameras are let us say IP driven cameras which are directly connected to the cloud. And this cameras is now capturing the video of the CC footage, and then they are pushing it to the central server. Imagine if there is no connectivity. Imagine if there is a low bandwidth or low latency issues and everything will be there. Then the actionable things that we are doing on top of the CC camera data will be missing. Let's say we are identifying, let's say he's a resident and he is a visitor and there are servants. And then, so like this, we have a lot of categories in facial recognition kind of technologies on top of CC camera data. And if we identify a trespasser, immediately an alarm has to raise. So that's how, let's say that's kind of system is there. And if they're completely relying on a cloud environment without having any fog environment in between or an edge computing in between, then if there is a loss in connectivity and if there is a latency in connectivity, if the servers are sitting somewhere in US or UK, then all of the data has to travel from here to the US servers and then it has to be processed in the central server. and there are tons and tons of cameras installed across, and all of these cameras are centralized, and everything has to be processed in the cloud. By the time it returns back the response that has he's a trespasser, so he may already pass that way, he may already pass that passage, and then we may miss that alarm. So that way, there are middle ways that are, if we can install, like kind of DVR boxes kind of environment, which are so sophisticated, and now we have an upgraded versions of it, where the complete footage will be processed in the local devices, and then it will raise the alarms faster because that is much closer, and it's in a local environment of the same network. And then eventually at the back end, it will push this data to the central server. So which means the complete CC footage is first storing, processing in the local environment, and then pushing it to the cloud environment. So cut short, we can say why we are using cloud is mainly to store the data, to identify the analytics. But we are moving the complete computing power, processing the data information into the edge device, which will take certain amount of load into the edge environment, and it will also make sure that it is timely, like the latency issues and everything will be taken care. So this edge computing is mainly been preferable where there is speed and then performance matters, and then it's basically to avoid any kind of congestion at the cloud, and then because of latency issues and all will be taken care. So on my right hand side, you will find a diagram where there are sensors at the at the field level, which are connected to a fog environment, which may be a local environment here. And here there's a certain amount of pre-processing will happen, work will happen, the task distribution or the data aggregation and all, and certain amount of processing will happen there. Then the refined information will be sent to the cloud. So we can also call it as a node. There are many nodes that we can establish for a couple of sensors, and then the data can be processed. So that's how fog computing works. And then what are the features of the fog computing is basically is one, it is basically works on hybrid model. It works both in a node, and then the data will be sent to the cloud. Then geographically distribution. Imagine an environment where the sensors are put across the entire world. Then the data has to be accumulated to different geographical locations. So where the nodes will be established, and then it will be pushed into the cloud. So this will be very much useful when there is a low latency, and when there is a real-time interaction. So it works very better. And then for mobility, I mean, when there is some sensors are moving around based on, let's say it's in ambulances or so, this fog computing helps them to immediately process the data and then later push it to the cloud. And then most of the interoperability things also been taken care. So I'll give you one more example here. So there are two things. One is uh, very timely data, medium timely data, and then low timely data. Let us say you are using WhatsApp, and then all your information is should be real time. I'm sending a message to someone, and then they're replying back. So this is a real time communication that happens, which needs a cloud interaction. But the backups of our chat may not need a real-time interaction with the cloud, wherein it will create a local backup at the edge device in my own device. And once in a day at midnight 2 a.m., it will push the entire backup into the cloud. So this comes under an edge computing mechanism wherein even all the messages need not to be sent to the server for immediate backups. The backups can be sent later as well. So what all the protocols that you are using in a certain environment has to be divided into very timely data, medium timely data, and then less timely data. And then accordingly, we should take decisions which needs to be directly pushed into the cloud, which can be processed at the edge first, and then push it to the cloud later. And one more classic example, maybe your toll gates. So when you are passing across a toll gate, you have a fast tag, right? So the fast tag, when you are actually reaching out to the toll gate, first thing it will do is to validate the fast tag, whether it is a valid fast tag or not, which has a sequence in it. Well, whether the sequence is passed or not, that can be processed at the edge. Then it will do whether the fast tag is blacklisted or is it active. that should be done in the cloud. Then the balance has to be verified, how much balance this FASTag is having. That has to be again, performed at the cloud. Then what they have to do is they have to deduct certain amount of cost to pass the toll gate, right? So that can be done locally first in the edge. Then the money will be deducted and the vehicle will be allowed inside, because it is a medium timely sensitive. So they will quickly do a certain operations at the cloud, and what all the things they have to record, like the money has to be deducted at so and so time, it has been passed by so and so FASTag ID and so vehicle number. All of these things will be recorded at the edge device. And eventually, as a batch process, all of these files will be pushed to the cloud within, for every 2 minutes, for every 3 minutes, the data will be pushed into the cloud. It is not a second to second operation they are doing, but their certain amount of work will be pushed into the cloud. So that's why when we are passing a toll gate, after 4-5 minutes, we'll get an alert, SMS or so that you have passed the toll gate or so. Because again, the operations are completely categorized into timely or non-timely, and then they'll process it accordingly. So when we are comparing the computing features of cloud as well as fog, mainly the latency issue is very high in the cloud when there is geographical locations comes into the picture. Servers locating in US, servers locating in India, or servers locating in Hyderabad also makes a difference. And we experienced it many times because we work on large scale implementations, performing more than 3 million transactions every day in a real time mode. So we understand how this latency issues work. Then when it comes to fog, since it is a local computing or edge computing kind of environments that we are using, so the latency issues is very, very low. And then the delays, because of the processing is happening at the central environment for all the devices at one place, and then it will take a little delay will be there. But in fog, it will be a local environment and a limited amount of devices are connected to it, so the delays are very low. And then location of server nodes is basically, it should be have an internet based connectivity, but in fog it's processing at the edge device or in the local network itself. There are multiple hops. It has to pass the DNS, it has to pass the firewalls, cloud, and everything, and it has to reach out to the server in the cloud environment, and the number of hops. But in fog, it's basically a one hop environment because it's completely locally available. Security, we can't define it because we don't know what kind of PII information is moving onto the cloud, and whether then even the information may not be permanently necessary, but still all of this information we are passing onto the cloud. But in fog, it's locally processed, so there won't be any problem. When large scale data is available, there is a high chances of data attacks may happen. When there is a less amount of data, the chances are very low to compromise, because end of the day, at what rate, with what cost, at what devices the attack is happening also matters. Location awareness in cloud, we don't have such. It will work anywhere, but yes, here there is a location awareness is needed. And geographically distribution, everything is centralized in cloud computing. But when it comes to fog, it's node driven. There are multiple nodes everywhere, and the information will be processed through it. Very few nodes will be there in cloud computing, but when it comes to fog, there are many nodes where the information will be processed. And mobility is very, very limited in cloud, but fog, they can still establish a local environment, but then they can take it as a mobility based environment as well. Real time interactions are supported in both the sides, and then from the last mile connectivity, it may be a leased line is needed for better performance and all. But in fog, we may have any wireless communication, even Bluetooth also works for it. And then how does this fog works? So when we establish these fog nodes, and I mean near to these IoT devices, within milliseconds, within fraction of milliseconds, we can process this entire information locally. But in the cloud, it will take minutes because the information has to travel all the way from edge device to cloud, and then it has to come back. So the applications varies from mainly from communication standpoint, or any kind of telemedicines or analysis can be done. With aggregation of nodes in fog, it's completely different. Like visualization is very simple and analytics can be driven. and then like IoT's information will be accumulated, data will be accumulated every second, but this information may not be needed to send it to the server. Every second's information can't be may not be needed to send it to the server. So all the information will be stored locally and then processed, and only the actionable data can be sent it to the server for further analysis to the cloud. So if we classify the information in a typical fog environment, what happens at fog and what happens at cloud? First, from the IoT device, the information will reach out to the fog, wherein all the pre-processing work will happen here. Within milliseconds, the data will be processed, and then uh, the data will be sent into the storage. In the storage, the data can be sent as a batch processing to the backend cloud servers, and it will aggregate all of this information received from various IoT sensors. Let us say the fire alarms. If they are a sensor which is accumulating the data to a local fog node, this entire devices will send an alert for every 10 seconds that it has not identified any fire in the room, and the device uptime is it is alive. Like, we should also know whether the device sensor is working or not, the smoke alarms are working or not. So this information will be sent to the node, fog node, but we don't need, like, let's say a lakh plus fire alarms deployed in a cluster. All this information every 10 seconds saying that this I am alive, the device is alive, and there is no fire, may not be needed to the cloud. So what it will do is it will push all of this information to the local node, local fog node, and it will process this information and send a summarized hourly report to the cloud server, like saying that in the last 1 hour, there is the entire sensor is live and there is no fire detected. So it will be a single record every 1 hour, which means hardly a 20 plus records to 24 records will be recorded in the cloud server. But in the fog node, it will be a every 10 seconds activity that will be performed, and then that will be stored in the local environment, and then eventually the data will be overwritten by the futuristic data. So that way, the information is uh, sent to the cloud, will be actionable. It can create reports accordingly. But in the event of fire, it will immediately send the alert to the cloud for to make it actionable, to send push notifications to all the security person around to actually move. I mean, take the action appropriately immediately. Yeah. So that's the other thing. So when it comes to healthcare, so they are now the systems are so evolved. The doctors are more of information driven, data driven. Say it is your lab report or a report from a specific equipment, right from CPR devices to oximeters. Everything is sensor driven. Everything is data driven these days when it comes to healthcare. So one classic example of how cloud and fog nodes are working out in the healthcare domain is there are sensors around in this COVID times wherein the patient or any citizen can actually place this on the chest, and then it will be like a sticker, and then they just need to put it. And then there is a certain amount of charging and all, we have to do it. And it will be a Bluetooth communication to our mobile phone, and this sensor will actually do some surveillance on a couple of vitals and parameters like oxygen saturation levels, and then it will do temperature checks. It will do a couple of more checks on it. And all of this information will be sent via Bluetooth communication. Now, this entire information sending it to the cloud in real time mode is not suggestible. I mean, the connectivity may not be great. This amount of information from millions and billions of sensors to a central system, processing it will be difficult. Latency issues will come. Then the timely actionable things. Let us say if there is any abnormality identified in the oxygen saturation levels or if there is an loss of connectivity. So that ways it will be a very critical thing for the patient. So what they're doing is they're pushing all of this information through Bluetooth into an edge device, and the edge computing is basically is our mobile phone. There a certain amount of checks, like it has all the thresholds placed for oxygen levels, for temperature checks, and so on and so forth. And then whenever there is an abnormality, it will immediately communicate the information to the cloud for further analysis. But however, for every 1 hour, the sensor information will also be sent to the central server stating, yes, this device is alive, the vitals are normal. In the last 1 hour, this is the status. A summarized view for future analytics of that patient will be sent to the command control center through the cloud environment for monitoring. So that way, critical information processing directly with the cloud may not be a good practice. Using some nodes or using some fog nodes or through edge computing, this can be computed locally, decisions can be taken faster, and for future analysis, for post-mortem of the data or for further analyzing of the data, that can be pushed into the cloud for futuristic things. There are various issues that has been, I mean, as industry driven approach. As per the market analysis, one is the self-caring services. As a user, I can take some level of sensors like a smartwatch to monitor my vitals and get some level of self-caring, and then there is no much penetration into the system of a real-time data monitoring systems for patients who are in hospitals. Then there's no real-time streaming engines. The data sources are very, very low. It's all distributed. It's all different softwares the data is holding. And then very, very limited data storage when it comes to analytics, identification and all. And then the security, the PII information is the most, the health information may be the most vulnerable data if it is not protected in a right environment. So what we need for healthcare applications is, first is the bandwidth, internet, then very reduced latency, which means the server should be very, very nearer. Then it should be energy efficient. And then how is the dependability? Like whether how many dependencies it has to work independently. Then the security of the healthcare devices, interoperability of information between devices, sensors, or the vendors, the privacy, and the scalability, how best we can scale all of these things. So uh, I can give you one more example of an ICU where a couple of sensors are connected to a patient to monitor his health. And then if it is directly connected to the cloud and all of this information is pushing onto the cloud, there are cases where within a minute or within 10 minutes of an alarm, the doctor has to attend that patient and get the CPR done and get him up again. So, but when we are using a cloud environment in a local low bandwidth, or when there is a big latency, like the hospital is located in Hyderabad and the server is located in California, and the information is passing on from here to there through a low bandwidth internet line. And by the time the cloud processed that information and identified, hey, that patient is critical, and it sends that alert back to the server, the we may have various many chances to lose that patient, or the alarms will be lost because of mainly criticality of processing speed, internet bandwidth, or latency issues. So when we have a fog environment established very near to the sensors, it may be in the hospital level, we can keep a fog node, and then the information will be processed at the node itself. Most of the computing alarms will be processed at the decision making capabilities will be pushed. The entire business logics will be pushed into the fog node so that the data will be real time processed in the local environment, and the alarms will be so effective. And at the same time, all of this information will be recorded at the fog node, which will eventually be pushed to the cloud at the backend, which is very less time sensitive data. I mean, it can be pushed at a later point of time also. And then so that the applications will be more helpful. Yeah, this is how typical fog computing in healthcare works. So these are the sensors. So at the field level, there may be wristbands, there may be infusion pumps, or glucometers or so, where these devices will be connected to a fog environment, which is established at the hospital itself. It may be another server, right? So it may be another node which has a decent computing speed. Now, these devices, sensors, will be connected using a Bluetooth communication or a Wi-Fi communication to the local fog established. And it will take care of many things like first monitoring layers and then storage layers and then security layers. So all of these things will be taken care. First, the data will be monitored, do some decision making business logics, and return back to the sensor that, hey, this is okay, this is not okay, kind of environment. Then all of this information will be stored, and then the information stored will be encrypted so that it won't be compromised. And eventually, at the batch processing method, it will use an internet based connectivity or a leased line based connectivity to push all of this data into a cloud environment. Once it is in a cloud environment, so the data science takes care of it. I mean, the lot of analytics will be identified, and the doctors can actually analyze this data much better, and then uh, the medication can be given that way as well. So this is how a fog computing actually works. So without fog, let's say in health applications, there may be a mobile phone or a home automation or a hospital or even in ambulances. A device, a sensor, will be directly connected to a cloud environment, and then the response has to come back. So this is how all these environments will be established. And internet, latency, storage. So these are the major three things. So one is the internet-based communication has its own kind of limitations, and the bandwidth, and then it has its own limitations again, and latency. If the servers are located somewhere in Dallas and then we are sitting in Hyderabad, that's a different story again. But when it comes to uh, a fog environment, you may have your local hops established. Like the mobile, there is a node established here. Here, a mobile Android tablet itself will acting as an edge computing device, where the device, all the information fetched from the smartwatch will be sent to the Android tablet using a Bluetooth communication. And at the device level, imagine in your smartwatches, all your information will be accumulated into your mobile apps, something like Google Fit or Samsung Health or Fitbit or so, and then the information will be processed there. And if you see, it will show you 10,000 steps or 20,000 steps a day, your heart rate, your heart points. So all of these things are showing in the mobile phone itself. And at the later point of time, this information will be sent to the cloud so that you can access this information from any phone, from your Google accounts, you can check your information. Imagine if we establish a direct connectivity to a smartwatch by inserting a SIM card here and establishing a data connectivity, pushing all of this information to the server. So that may not work. I mean, when you are walking in a non-connectivity area, in a cellar or in some agency area, or when there is no connectivity, then you will lost those information. So that's where this hybrid model of establishing fogs. Your device may be your edge computing device, or you may be establishing a node for the entire information processing in that premises, and then you can push it to the cloud. So that's how a fog environment works. So it's a comparison from fog, cloud, and IoT devices. Fog is basically a mobile user. Cloud is a general internet. I'm accessing my Gmail or so. I can directly access to the internet. I don't need any node, fog, and node in between. But when there is an IoT device, it needs a certain amount of data to be processed. IoT information can actually uh, extract the information. It can fetch the information from the sensor, and it needs some computing device to process that information. So the server nodes are very huge in both the cases of IoT and fog. And then cloud, it's very limited the number of devices. And both are distributed devices, but cloud is a centralized one, and most of the information will be localized. It will be processed at the edge devices, and it's based on the end devices information will be gathered. and it's globally driven. All of the information is real time, it will be pushed. So working environments, I mean, it's all generalized. I mean, indoor you can sit, and then where there is a decent connectivity, you can use a cloud environment. But when there is criticality in information, timely driven approach, and issues with the bandwidths and all, a fog or an IoT environment is a better suit for it for the application. So all our real time interaction supported, all our mobility supported. Then the storage basically is a lot of data will be accumulated in IoT and fog because it's a second to second, minute to minute kind of information will be accumulated. But in the cloud, it will be pushed everything in months and years, so that yeah, so the services will be smoother. There is Cisco is a father of this fog environments, though they have done this innovation. And then cloud, it's pretty much there everywhere now. Google is having, IBM is having, Microsoft is having, Azure, AWS, or Google Cloud. So many other cloud players are there. And IoT is a typical sensor. It's a physical device. So this ARM or Bosch are typically building this kind of sensors. So I think I can summarize it. So basically, with a certain amount of examples, when there is a IoT device, when there is a sensor, and this information has to actually move on to for into a cloud, we should actually evaluate it first whether this is a critical information which very timely or medium timely or low. I mean, it's not timely dependent. Then based on that information, we can decide, yes, this environment can be worked out with a fog environment or not. So where there is a medium and high timely driven approaches, so we can use fog nodes for quicker data processing and then push all the data information into the cloud at the later point of time. Yeah, so that's my conclusion, and then I'm open for questions.
Yes, ma'am, I'm here. I'm looking at the chat box if there are any questions.
Yeah, great. I think I'm done with the session, ma'am. So we'll just wait for any questions to raise.
Vamshi, so in fog computing, whether any hardware requirements are there, directly we can use Amazon, IBM clouds directly to do some applications by using fog computing.
So basically, Amazon and Google and IoT, I mean, these kind of devices are again a cloud-based environment. But yeah, Amazon and these guys are also providing certain amount of nodes to process this information. But typically, that should be very, very closer to the our wherever our IoT devices are there. We should make sure that the devices are the nodes are very closer to it. A local environment is the best suit, or our edge device, our mobile itself can actually process a lot of information in edge computing. We can use it also as a edge computing device. Then eventually the information can be processed into the cloud.
Better or processing entire thing by using GPUs is better.
Madam, sorry, I lost you for a second. Could you please come again?
Instead of doing edge computing, which is better, edge computing or processing by using GPU? Which one is better?
So basically, I suggest to go with a hybrid model, madam. So let us say, I'll give you a classic example of it. So we have built a facial recognition based time and attendance system as a replacement of any biometric systems, where we are using the capabilities of the edge device and also the GPU power at the back end to process the data. which means, let us say, when somebody is facing the camera in front of the device, whether it is a valid face, whether the eyes are open or not, whether there are multiple faces in the screen, all of these validations we moved on to the edge device. The edge computing can actually process all these three: eyes closure, valid face, whether there are multiple faces, all of these things will be taken care at the edge computing. Then the photograph will be sent to our cloud, GPU cloud, where in the GPUs we will validate, yes, whether this is a live face, whether this is an photo of a photo, video of a photo, whether it is a real photo or not, and then whether this face is matching with any of the existing repositories, and then we'll mark the attendance. So that way we are moving certain amount of operations at the edge level, because those are the primary things. If somebody has closes the eyes and somebody other guy is actually showing their face when somebody is sleeping, so that should not be processed. So a certain amount of checks moving into the edge device will actually take our processing time very down, and then the basic validations can be done at the edge device itself. So always a hybrid model, because we have tried doing everything at the cloud, but we what we felt is, from the response time standpoint, when we use a hybrid model with edge plus GPU, gives us a very better efficiency.
Could you please suggest a few good edge devices?
Sorry, madam.
Suppose if we want to purchase some edge devices in our lab,
Okay.
or anyone wants to build some applications by using edge computing, what are the minimum requirements to have with us to develop some applications by using edge computing?
Okay, so these days the computing power of a mobile phone is almost reaching out to a computer environment, madam. Like depends on the kind of data that we are processing. Whether this is an image processing data, are we using a machine learning or an AI based technologies, or what kind of information that we are going to process. So eventually, let us say earlier, when we are doing some validations at the device level, we only validate a certain amount of parameters, whether the number sequence is right or not, whether the finger capturing value, the ratio is okay or not. So it's only script driven data points will be validated. So for that, we just need a very, very, very low computing speed. But when it comes to deep learning based mechanisms that we are doing now, I think every mobile that we are using today is having decent amount of computing power with a certain amount of storage. So I think any kind of computing device from the mobile environment with decent amount of storage and RAM and computing power is fine. But when it comes to the GPU environment, the backend, that also plays a major role, because 20-30% of the work will be done at the computing will happen at the edge device, but the rest of the information will be processed at the backend. So that way we need to understand how many CUDA cores we are having, how much of memory that we are allocating to these GPU servers for processing. I think AWS already solved it. AWS has around 3 to 4 different variants to process the information, but it's a little costlier compared to you establishing a physical server in your own environment. I think Tesla is having some models which is performing better. So we are processing around uh, 20 million transactions every day using some deep learning techniques for a couple of banks for their internal data processing engines. So we have established a very big cluster of GPUs for processing the data, madam. So the edge computing plays a very minimal role. So any mobile, and we have a limitation, like any technology that we build has to be compatible with all the mobiles available in the market. We have done it recently for pensions. Pensioners has to submit a life certificate uh, wherein they just need to take a selfie, and then we do a couple of checks whether the face is a live face or a fake face, then whether this face is matching with our repository, then his life certificate is issued. Earlier, they have to reach out to a government officer, sign the document, get it, and then submit it in the pensions office and all. So now it has been moved electronic. Same way with degree college admissions. Earlier, there is a certificate verification process and everything. So now we moved on to a completely mobile-driven approach. Take photographs of the certificates, take selfie. We are validating with the data sources and then approving it. Same with driving licenses and all RTO department. It is completely alive in Telangana. Like if you lost your driving license, you just need to install that app, take a selfie, do the payments, and then you will get a duplicate license to your home. So in all of these cases, the mandate that we got is whatever the technology that we built should be applicable for the maximum number of devices in the market. So we are not able to process it for Android 4.0, any Android 5.0 and above, everything has to be supported. Even the least capable camera quality, that is 2 megapixel, should also be supported. That's the mandate that we got from the governments, and then we achieved it with the highest accuracy, madam. So I can say any technology that is developed should be compatible with any kind of mobile phone. And today in the smartphone environment, for running the minimal, validations, I think this computing speed is pretty much fine to process it.
One more question from Miss Renuka Devi. Is there any limit on memory requirement in fog computing and also on processing limit?
It again depends on the kind of data that we are processing, whether this is CCTV video surveillance data that we are processing. It needs the highest level of computing speed and graphical speed to recognize the information at the fog level, or to store that video surveillance data into the hard disk. It may need terabytes of storage at the node. But when it comes to the sensors information, it is very, very minimal. It is KBs of information that we get every second. So it depends on what kind of information that we are processing, whether it is a video footage, whether it is a data record that we are inserting into the system. The fog records will be established. But however, this information will be sent into the cloud on a timely basis, and this can be overwritten. We don't need a permanent storage at a fog level. The information will be sent to the cloud eventually, and that will be overwritten. So that's how even the CC camera footages are only available for 30 days in a DVR box. And the 31st day, the first day record will be deleted and it. So if we connect an FTP protocol into the cloud environment, all this footage will be moved onto the server every night, so that there won't be any limitation of the fog, because it's a temporary data that we are storing there.
One more question from Mr. Naveen Kumar. Can we call fog node as IoT gateway? If no, how could we differentiate?
So in a way we can call it so, like it's like a gateway, but the gateways are basically meant to actually push the information to the right devices at the right time. So, but here we're also having a couple of more activities will be performed at the fog. So all the operations of a gateway can be taken care, but it has much better capabilities to process that information as well.
Once again from Ms. Renuka, could you please suggest a few latest applications of fog computing?
So mainly from the healthcare domain, recently companies have built sensors wherein the information will be accumulated from the sensors to the edge computing devices, and the information will be processed then and there itself to raise the alerts. Only the summarized view is sending it to the cloud. So that's a classic example. Even in fast track toll gates, when you are passing a toll gate, the information will be accumulated into a toll gate booth, wherein the entire information of all the toll gates will be processed in the local node, and then it will be pushing it to the server. So these are the two classic examples of recent fog applications.
Savia?
Yes, ma'am. I'm here.
Is there any?
Yeah, there are a few questions, sir. I'll ask them at once so that you can see if they overlap and you could answer them at once. are there any limit on data points and how to compute processing time in fog computing? And are there any existing architectures for real-time implementation of fog computing?
So basically, from how much of memory? I mean, could you please come again?
Are there any limit on data points? The first question.
Okay, so are there any limit on the data points? No. Basically, first we need to evaluate what all the information that we are accumulating and how much of KBs of information are getting. I mean, we are getting it, and then what level of information is getting executed. Let's say how many queries we are executing, and each query how much time it is taking, and how much of processing speed it will. So we have to do a certain amount of stress test and load test while we develop these applications to identify how much of computing power this is occupying for each query execution, so that we can identify what level of computing we have to establish for the node. And for the architectures, it's pretty much available in the internet. You can find many standardized architectures of fog environment implementations.
Thank you, sir. I think that's all we have for the Q&A session here.
Great.
Thank you, sir, for sharing your insights on edge computing, their advantages and applications. I'm sure the audience could establish the difference between fog and cloud computing, which has been a haze for many. Also, your thoughts and facts about the requirements for fog computing in the healthcare applications was very informative. Thank you for being patient and answering all the questions here. Somebody also told that it was a great session with all the latest applications being told.
Thank you so much.
Yes, yes, sir. We would like to present a virtual memento to you.
Oh, great. Thank you so much, madam. Thanks for giving us an opportunity to actually be a part of this IEEE event. Yeah.
Thank you, Vamshi, for sparing your valuable time, even though I can understand how much busy you are. Even though you are that much busy, you have accepted our invitation and delivered valuable insights about fog computing, which is latest technology. I think all the participants have learned something from your talk. So please, whoever is having any issues regarding implementation, Vamshi is always will help to develop applications. Thank you, Vamshi. Thank you.
Thank you so much, madam. Thank you so much. Yeah. Yeah, Sadia, I think I can leave.
Okay, Vamshi. Thank you. You can.
Thank you so much, madam.
Okay.
Ma'am, we couldn't see the virtual.
పెట్టే కదా షేర్ చేసా కనపడలేదా
Some.
మరి నువ్వు నాకు చెప్పలేదు సార్ని లీవ్ వెళ్ళొచ్చు అంటే అయ్యయ్యో నేను షేర్ చేసా సరే
Yeah, I will mail to them.
ఓకే ఓకే యాక్చువల్లీ షేర్ చేసా మరి అప్పుడు ఎందుకు మిస్ అయింది మరి ఓకే అమ్మా శివతేజ సార్ జాయిన్ ఓకే
Yes, sir.
కుడ్ యూ ప్లీజ్ ఇంట్రడ్యూస్
Hello, sir. Happy to have you here. So our next talk is by Mr. Shivateja Kakileti on machine learning for breast cancer diagnosis. Mr. Kakileti has more than 5 years of experience in AI/ML for medical imaging. He is currently one of the key data scientists at Niramai Health Analytics Private Limited. He previously worked on the healthcare analytics group at Xerox Research Center, India, as a budding scientist for 1.5 years.
Hello, I think Sadia? I think she is having network issue. I request Shivateja sir Please, please take the session. Hello, Shivat sir.
Oh, sorry, I'm on mute. Okay. Thanks, Padma.
Okay, sir.
Yeah. So can I start the presentation?
Yes, sir. Hmm?
Presentation.
Yes, sir.
Okay. Yeah, good morning, everyone. So I'm Jyothi, I'm a data scientist at Vignana Health Analytics. So in this talk, I will briefly discuss the applications of machine learning for breast cancer diagnosis. Before I go into the details, I will introduce the problem of breast cancer. Breast cancer is one of the leading causes of cancer deaths among women all over the world. According to World Health Organization, 627,000 women lost their lives to this disease in 2018. When you see the statistics in developed countries like United States, the survival rate is 80%. However, in developing countries like India, it is merely 50%. In 2018, approximately 162,000 women were diagnosed with breast cancer in India, and every 1 in 2 diagnosed women lost their lives to this disease. Research shows that early detection can improve the chance of survival. Conventionally, X-ray mammography, ultrasound, and MRI are used for breast cancer detection. X-ray mammography uses X-rays to measure the breast region. So it works on the principle of looking at the density between the malignant and normal tissues. But when the tissue surrounding the tumor region itself is dense, it might not be applicable. So it's typically recommended for women above 40 years. Ultrasound uses sound waves to study the structural properties of the malignant lesion, but the accuracy of it when we use standalone, it is low. So it is typically recommended as an adjunct to mammography. MRI uses the magnetic radio waves to study the internal anatomical properties of the breast region. It has high sensitivity, but it has very low specificity. So again, it's used for high-risk women or women with dense breasts. The combination of these 3 imaging modalities have shown a reduction in mortality rates, especially in high-income countries like United States. But implementing this in countries like India poses many challenges. These are high-cost equipment, requires dedicated space, and are not easily portable. And for both imaging and interpretation, high-skill expertise is required. And in countries like India, the radiologist to patient ratio is 1:10,000. And one other reason for women not opting for breast imaging is embarrassment to undress in front of a technician. Due to these reasons, even though X-ray mammography, ultrasound, and MRI are present, in countries like India, the mortality rates are very high. So at Niramai, we propose the use of breast thermography, which is nothing but a measure of temperature values emitted from the breast surface. So what happens when there is a cancerous tumor inside? It requires higher metabolism to grow, which is facilitated by high increased volume of blood towards the vicinity of tumor. This process is called as angiogenesis. When we have this much metabolic activity at the tumor vicinity, it generates more heat, which can be traversed to the breast surface through venous convection and tissue conduction. With the latest infrared thermal cameras that are available in the market, we can detect minute temperature variations up to 0.02 degrees centigrade. So it can help us to study heat variations due to different abnormal conditions that might happen in the breast region. So we use this principle to study the malignancy in the breast region. So by using breast thermography, we have advantages when compared to conventional imaging. Since what we are doing is we're just collecting the heat that's emitting from the body, it is completely non-contact and non-invasive. And we are not inducing any external radiation like X-rays, where X-ray mammography, where we use X-rays. So even though there is no cancer, using X-rays can increase the chance of getting cancer. And also this is a very portable, light, small and low cost imaging device which might be suitable for countries like India. And by controlling the camera remotely, we can make this entire breast imaging a privacy aware, where technician need not see the undressed woman. And it can work for women with dense breasts as well. But one of the main challenge with breast thermography is the interpretation. What we get from thermal cameras are the raw temperature values. So for visualization purpose, we convert these temperature values into color palettes. As you can see in these images, these are the images of the same participant, but are converted using two different color palettes. So one is from 25 to 39 and the other is from 28 to 36. As you can see in one image, we are not seeing any heat pattern. So here red and white means high thermal activity. So we're not seeing much of high thermal activity in the breast region. But when we change this temperature palette from 28 to 36, we can clearly see some high thermal activity around the areolar region in the breast region. So it requires high expertise as well as it is subjective, the analysis of breast thermography. And also the high thermal activities can even be caused due to benign conditions such as fibroadenoma and ductal ectasia. So here in this case, machine learning can help in alleviating the subjectivity that might happen with human interpretation, as well as improving the accuracy of breast cancer. So to build such a computer-aided diagnostic system, at Nirama we had multiple machine learning modules in place. The first module is as soon as the patient data arrives, we need to check whether the images are good or bad for analysis, because it might happen that the images are not so focused or the images doesn't contain proper thermal data. So we have one classifier that classifies the image as whether it's a good image or a bad image for analysis. And next we have auto tagging. So to image the breast region, we need to capture multiple views of the subject. So many times what happens would be the technician who are capturing these images, they might not label these images properly. So we have an auto tagging classifier which automatically labels these images given a view. And as you have seen in the previous images, we are capturing the region from neck to abdomen. And for analysis of the breast region, we need to do the region of intersegmentation. So we have a ROI segmentation module in place, which segments the breast region given a thermal image. And once we get the breast region, we identify the high thermal activities which are displayed as red or white heat patterns. And from that, we extract features which can be used for classification of malignancy or normal. And once we classify it, we also classify the malignant tumors as hormonal positive or hormonal negative, which is an important biomarker for treatment planning. So to summarize, what we get is a set of thermal images, and we have a computer-aided diagnostic tool which automatically interprets these images and generates a two-page report describing the heat pattern in the breast region as well as what are the chances of malignancy. So what are the main challenges when dealing with medical data? Data collection is costly, time intensive, and involves stringent regulations. Unlike any other object detection or any other classification problems, we might get data easily by going out and getting the images. Like if you want to classify the traffic signal, we can go and capture the images. But for data collection in medical imaging, we need to take proper ethical approvals from the hospitals, and we need to take the consent forms. So this is costly as well as time intensive. And even we get the data, getting ground truth or the labels for each of this data is another task. Because for some of the classification tasks like diagnosis, we might need to follow up with the participant for a certain period. So for example, if you want to know whether the patient has cancer or not, currently there is no imaging modality that is 100% accurate. So we need to follow up the participant with multiple imaging modalities and ultimately biopsy, which is nothing but the tissue sample analysis. Similarly, if you consider anything about treatment monitoring, so we need to follow the participant for the entire treatment course to know whether the treatment is working or not. So that way the data collection and the ground truth is time intensive. And depending on this data constraint, we need to decide what choice of algorithms we need to go. Whether we need to select feature-driven algorithms, which are nothing but we use domain knowledge for the classification, or the data-driven approaches, which can learn from data. So in this talk, I'll be briefly presenting about our journey in one of the problem, which is region of interest segmentation. The agenda is to understand the problem, and I will discuss a feature-driven image processing approach and a data-driven learning approach. And we discuss both the merits and limitation of both these approaches. So before I go to the details, are there any questions till here?
No, sir. You can continue, sir.
Okay, sure. So these are the thermal images that are being captured by a technician. So we typically capture 5 views as seen in this slide. So this is called frontal view. This is left lateral, left oblique, right oblique, and right lateral. So we capture these multiple views so that we can image the 180-degree of breast region. So if the tumor is on sides also, we'll be able to see in some of these views, even though we miss in frontal view. So the task here is to segment the breast region as we are capturing the entire region from neck to abdomen. But unlike traditional object detection algorithms, we don't have any strict boundaries. As you can see here, there is no upper boundary or a side boundary. And even with human segmentation, we found an inter-observer dissimilarity, that is a correlation between the ground truth segmentation between 2 human experts is 91% alone. And when we got this initial problem, we only got data of 50 subjects, that is around 250 images, and we have to build a robust algorithm using these 50 images. So we use domain knowledge to build such algorithm. So the feature-driven approach are nothing but any algorithms that we use based on the domain or statistical knowledge to develop the algorithm. So we approximated the breast region into by 4 boundaries, which are lower boundary, side boundary, and middle boundary, and body boundaries. And to detect the lower boundary, what we have seen is that in most of the thermal images, we are seeing this high thermal activity just below the breast region. It is called inframemory fold. This is always found to have higher temperature. So what we have done was we detected this inframemory fold using histogram-based thresholding. We have also tried age-based techniques, but we found that region-based algorithms are better for this approach. So we detected this high thermal activity region that is below the breast region, and we took the upper boundary to get the lower boundary of the breast region. And to detect the upper boundary, we have used acceleration. As you can see here in this image, there is a slight, there is a sudden curvature change from hand to breast region. So it forms an inflection point. So what we have done was, by taking the body boundaries, we found the inflection points in that curve. And we took the uppermost inflection point and we got the upper corner of the breast region. And then we just assumed the straight line along the x direction to get the upper boundary. And we also found that if you go with a heuristic, that the upper boundary lies above the inframemory fold within a distance of half the width of the abdomen region. If you go with that heuristic also, we're also getting a decent results in segmenting, getting the upper boundary of the breast region. To get the side boundaries, we have found the body boundaries. So for this, we used OTSU segmentation, which is a foreground classifier. And once we get that side boundary, we have taken the body border of it. And the final, to get the final boundary, which is the mid-body boundary. For a frontal view, as you can see here, both the breasts are symmetrical. So the middle boundary can be approximated as the boundary that divides both left and right boundaries in 1:1 ratio. The same logic can even be used for lateral views. And using rotational geometry, we can find the shift in the boundary, and we found that this would be close to 1:2 ratio for oblique. Once we get these four boundaries, we take the region that is enclosed within these four boundaries. And that is the final brush region. When we have done this, we got reasonably good results, especially when the imaging protocol is followed. But when we deploy in a real world scenario, and the imaging is done by minimally trained technicians, the accuracy is low. We only found 70% dye similarity. So these results are highly dependent on the imaging protocol, mainly due to the use of low-level features or simple heuristics for segmentation of breast region. So what we have done is, from the image processing approach, or whatever segmentation we're getting, we displayed using a polygon. So now the technician can adjust the region if they think that whatever the algorithm has predicted is slightly wrong. So they can modify it by dragging the vertices. What it has done is it has reduced the overall time for segmentation. And with this initial setup in multiple hospitals, we obtained 1,000 subjects. And now the question is, can we use data-driven approaches like deep learning to get more robust segmentation? So before I go to the details, are there any questions?
No, sir.
Okay, sure. So deep learning is a data-driven approach which can learn from available abundant data. It has shown state-of-the-art results for classification and segmentation problems. So below is one example. So the task here is to classify the input image. So if you go with the feature-driven approaches, we used to use what is the strokes length and how many times there's a change in curvature. Depending on that, we can classify whether it is a digit 2 or whether it's a digit 1. Because if it's a digit 1, you only have one change in the curvature. But for 2, you will be having multiple. At the same time, we can use domain knowledge as the loops that are formed. So the loop which you're seeing here would be formed for only certain digits like 2 or 8. So detecting this domain knowledge features, we used to get reasonable accuracies, but again, all these are low-level features. So what deep learning has done is automatically learning these features from the available data. So CNNs are a class of deep learning networks which eliminates the need for manual feature engineering for images, which is nothing but feature-driven approaches. They can learn the complex features with the help of the depth in the architectures. So instead of relying on low-level features, it extracts high-level semantic features. I think there's a question.
Yes, sir. So where can we find the data sets for breast thermography?
So for breast thermography, there is a publicly available data set from Visual IR Lab. So you can search for PROENG, PROENG, and Visual IR. So they have a publicly available data set with close to 100 images.
Okay, sir.
So now we have the deep learning models, but how much data we need to train such deep learning models? Because we don't induce any domain knowledge features, and it learns from the image pixels data that is available. It has millions of parameters involved in training a deep learning architecture, but we only have 1,000 subject data, which is approximately 5,000 images. So the question was, is that sufficient to train deep learning architectures? So what we have done is, before starting our experimentation, we augmented our data. So data augmentation is a standard principle in many of the deep learning architectures, where we try to improve where we try to increase the overall data. So some of the augmentations what we have done were, we have used Gaussian noise addition. So this you can assume as when we capture the images, there might be interference from different subjects or different objects in that room. So those can be mimicked by Gaussian noise addition filter. So what we have done was we have taken the existing images and added Gaussian noise with different standard deviation. This has helped our algorithm to work even in case of any inference from other objects or the subjects around the participant. And the next one is random crop and resize. So as you can see, we are capturing the image from neck to abdomen, and this region will be dependent on the technician who is capturing. So some technicians might capture from somewhere here to here, and some technicians might just go from left side here to here. So to incorporate these operations, we have performed random crop and resize, where we randomly crop the images to mimic these possible scenarios. And the other operation was random region insertion. So what here we have done is, because the breast segmentation is independent of the heat patterns in the breast region, so we have inserted some high thermal activities inside the breast region. So we have taken the breast region and we have randomly changed the pixel values from being low to high or high to low. So this would help us to learn the scenarios where there are malignant lesions or where there are benign lesions. And the other task was to make our algorithm robust to different thermal cameras. So thermal cameras comes with different sensitivity. Sensitivity means that what is the temperature difference between 2 pixels, how accurate it can learn. So we have modified the temperature sensitivity from 0.02 to 0.25 to work with different thermal cameras as well. Along with these augmentations, we have flipped the images so that right breast becomes left breast and left breast becomes right breast. So as you can see in this image, here the right breast, when we flipped, it became a left breast image. So to make it robust, we have flipped this all the augmented images, and we got 2x amount of data. So now with this, we have trained a deep learning architecture. So we have went through different algorithms and found that encoder-decoder architectures are found to be better for segmentation of region of interest. So what encoder-decoder architectures does is that, so there will be encoder layer which tries to downscale the images and learn the high-level latent feature vector. And from this feature vector, we upsample to get the final segmentation output. And at each level, the encoder stage is connected to decoder stage, which could help in better reconstruction of the thermal image or any medical image. And we can see skip connections at each of these stages, which would help in avoiding gradient vanishing or gradient explosion problem. So we have tried different variants of the architectures like UNet, VNet, and without the skip connections, but we found that overall having a skip connections helps a better learning. So the main problem when we're training with this architecture was the ambiguity in ground truth. So if you're feeding a frontal view, the output is both the breast regions. But when we're feeding a side view or an oblique view, the output is the only one breast region. So how should we make the convolution neural network or the VNet architecture to learn better for both these images, that when we give frontal image, it has to predict both left and right. Whereas if you give oblique view, it should predict only the dominant breast region. Even the other breast is slightly visible. So for this, what we have done was we have trained the architecture by just feeding the left views. So we give this image and just give the left breast segmentation as a final output. And now to get the right breast segmentation, what we have done was we flip this image and fed it to the architecture. So when we flip the image, so the right breast becomes a left breast. So we'll be getting the left breast segmentation, and when we flip it back again, we'll be getting the right breast segmentation. So with this architectural setup, we were able to train the architecture, and we specifically used VNet architecture with 5 stages. That means we have 5 downscaling and upscaling layers. And we just train the architecture by feeding the left views, and the right views are correspondingly flipped for getting the right breast segmentation. So to measure the loss that whether deep learning architecture is learning properly or not, we have used a modified dye similarity. So dye similarity measures whether any of the two subjects or two objects are close enough or not. So we have modified it by introducing one more penalty term, which you can see in the bottom, that says that the distance between the centroid of the ground truth and the predictor region should be as close as possible. Since we have only one breast region here per image, so taking the centroid of the breast region works here, but it might not work for images with multiple objects in the image. So when we train the architecture, even though the subjects are too far or too close, we are able to get the breast region accurately. You can see in these images, the blue region is the predictor region and the green is the manual segmentation. So irrespective of the depth or irrespective of the view angle, the proposed segmentation has worked well. However, if you see when compared with the heuristics based or image processing segmentation, it was not accurate when the inframemory fold is not visible properly, or even the view angle is not proper, because if you remember, we use 1:2 ratio for oblique view segmentation. So that only helps if the view angle is perfect 45 degrees. But if it is not at 45 degrees, but if it is 55 degrees, there might be a shift in the middle boundary. And then, that could lead to improper segmentation of breast region. And when we measure this, we have obtained a dye similarity of 92%. And this is greater than observed 91% dice correlation between human experts. So this tells that the proposed algorithm is as close to human expert. And even when the images are improperly captured, the algorithm is able to predict the segmentation region properly. And to answer the question on at what stage we need to go with deep learning, or at what stage we should switch from feature-driven approaches to deep learning approaches, we have found the dice index metric for different size of training data set. So we have divided the data set into chunks of 250 subjects, 500 subjects, 1000 and 30,000 subjects. And for each of these subjects as a training data, we have measured the performance of the architecture. As you can see here, the performance of the architecture has increased up till when we have the size of training set as 5,000 images. After that, it's more or less saturated. So what it tells is, we have a data more than 5,000 images also, the architecture is not learning anything new. So if we want to have the better performance of the architecture, we need to have a different variety of data. So using this peak point, wherever the curve plateaus, we can switch from feature-driven approaches to a data-driven approaches. So the takeaways data is key constraint in medical images in attaining better accuracies. And the traditional machine learning approaches can help in bootstrapping initial deployments. And deep learning has helped us in improving the accuracy from 70% to 92%. But the catch is that the amount of data we need to attain that accuracy is very high compared to an image processing approach. So as you found out, most of the results are dependent on the amount of data we get. So the other way to improve data is with data synthesis with generative adversarial networks. So we have done normal augmentations, but those are standard augmentations, and the network can learn those augmentations with very few operations. And as you have seen in the previous graph, it has saturated at 5,000 images itself. So we need a wide variety of data. So for that, we have constructed a generative adversarial network to artificially simulate the data itself. So here, I will just briefly explain the architecture. So here the input of the input to the architecture is a Gaussian noise. So what the generator does is, by taking this Gaussian noise, it randomly generates any image. And we have a discriminator which takes the actual breast thermal input and the generator output as an input, and then it classifies this input, this whatever the green line is as breast thermal image and the red line as non-breast image. So after training for certain epochs, what generator does is it tries to generate the images as close as possible to the real breast images so that it can fool the discriminator. So when we trained this entire architecture for 150 epochs, we were able to get breast thermal images that are as close as to the real world images. So as you can see, this is an output which is generated by the deep learning architecture. And the interesting thing here was we were able to get different variations of data and also different view angles, different possible hotspots or high thermal activity regions. Yeah, thank you. I'd be happy to take any questions on this.
Yes, sir. Thank you for the wonderful session. There's a question that in CNN architectures, we have different models like Lenet, ResNet, etc. So how did you identify that this is going to work the best for you, or how do we identify which is going to work in favor for our research?
Right, that's an interesting question. So I think it depends on trial and error approach. So what we have done was we have when we got this problem, we tried different deep learning architectures like fully connected networks and encoder decoder architectures and other segmentation approaches, and we found that VNet architecture is found for this approach. As you can see, there might be pixel-based segmentations which classifies each and every pixel whether it belongs to breast region or not. But one of the challenge there was the computation time. So if you classify for each and every pixel, so for entire image, you need to, for entire image of dimensions 320 by 240, you need to have a 320 by 240 classification. So it takes more time for those kind of pixel-wise classifications. So we went with encoder-decoder architectures. And under encoder-decoder architectures, we found this recent architecture called VNet performed well for this breast thermal segmentation data.
Okay, sir. Thank you. I think that answers the question. And there's another question saying, is this solution already being implemented in the hospitals? Is it already adapted?
Right. So currently what we have done was we have deployed this solution in 30 hospitals around India. And as soon as we get this segmentation, like whenever the technician uploads the images, the system automatically predicts the segmentation. And if the technician adjusts his breast region, that event is noted, and we use that to retrain our architectures. So we perform active learning on the go whenever the technician adjusts the breast region.
Okay, sir. Good to know that. I think there are only so many questions. Padmasai ma'am, would you like to ask anything else?
Sir, when we are implementing deep learning algorithms, so we require systems having high-end capability. How can we handle such issues?
Yeah, that's a good question. So Typically, we at least in Niramai, what we do is we go with the cloud-based GPUs, and there are these preemptive sessions. What it does is that whenever there are freely available GPU sessions, they can get you for low cost. So the overall cost we can save with the preemptive sessions are almost 90%. Compared to a non-preemptive session, which is a dedicated GPU for the experimentation. So what they do is that if no one is using the GPUs, they give it for lower cost. But the only problem is that whenever someone needs the GPU, they will just give you 2 minutes notice, and you should stop the simulation, and then they will take out the GPU. So going with preemptive sessions would help to save the overall cost.
Okay, there's a connected question here. Can cloud computing come to rescue in such situations to decrease the computing power?
So it depends. The cloud computing wise also it is pretty costly when we need high GPU. So whether it is a in-house GPUs or a cloud GPUs, it's a trade-off between the cost and the infrastructure maintenance. So if you're going with like 3 years, 4 years GPU usage, you might feel to have an in-house GPU to lower the overall cost. Otherwise, we need to pay too much money to the cloud, either AWS or GCP.
That is all we have for the Q&A session. Ma'am,
Sir, could you please suggest few GPUs which can any education institutions can acquire so that we can do projects for students as well as faculty members they are working on deep learning.
Okay. So what we have found in our experience is that NVIDIA Tesla T4 is low cost and as well as its performance is better compared to other devices. So at Nirama, we use Tesla T4 devices.
Sir, how to test which algorithm is best suited for these applications? Can you explain a few lines about that one? For example, I am using CNN for my breast cancer. For example, I am doing some ECG processing, some other algorithm. How to select best algorithm based on the application?
Yeah, that's a very good point. So in this case, what we have done was we have used dice similarity metric for the comparison. And so why we use dice is that as we have mentioned in the previous slide, the breast segmentation, the overall region, even with human experts, there's a variance because there are no strict boundaries. So we need an accuracy metric that is less sensitive to this kind of variation. So what DICE index measures is the percentage of overlap area. So that is the reason we have taken the DICE. But for other classification problems like breast cancer malignancy prediction, we might need to go with categorical cross entropy as a loss function or the overall accuracy as a loss function. So it depends on the problem. So if it's a highly imbalanced data set, going with a categorical cross entropy loss would be misleading because if you have most of the samples as negative, that is like if you see in the image, most of the pixels are background. So there is a high imbalance between negative and positive samples. So going with a categorical loss entropy, even though the accuracy is high, the prediction of the breast region pixels would be low. So that's the reason we went with the DICE index, which measures the similarity between objects rather than pixel level accuracy. So that answers the question.
Yes, sir. Thank you, sir.
yes, so we if there are no more questions, sir. Okay, ma'am.
Sir, one more point. If any, so actually we are facing all education institutions, not only me. So for getting medical data, we are having a few hospitals access here. So I think in Bangalore and Chennai, we have a lot of scope to interact with many hospitals. So is there any scope to collaborate with your organization so that so we don't want anything, or not only me, whoever is attending this event, all the education institutions, they work on your problem, whatever small data is problem you are sharing to them. We can build some applications which is useful to you as well as your organization. Could you please suggest us what can we do?
Sure. So coming to the breast thermography data set, it's already available. So from a recently it became a trend to open source the existing data. So for some of the problems Nirama is working on, we also start open sourcing the data. But as you know, all this data comes with the stringent regulations that we should not be sharing with third-party users. But I can discuss with internally and then get back to you on the Nirama data set. But most of the main reason for not availability of medical data sets publicly is the stringent regulations that that are in place when we collect the data. So we should not be sharing with the third party users. But I think we now have data where we have the permissions, but I need to discuss internally to make it open source. But recently, we have made the X-ray data of the chest X-rays as open sourced. I can share you those data.
Yes, sir, please do. That would be great. And also, during the presentation, you were telling that you told about a source from which the data can be available.
Right. It's a pro data set. Yeah, I can share that link as well.
And also the presentation, if that is okay with you.
Sure.
The participants have been asking.
Okay. So I can share the slides as well as the links to the publicly available data set. And there are, I think, medical archives where you can directly search for all the medical data. Like, for example, if you want to have X-ray mammography images, NIH from US have almost 10,000 mammography images. Similarly, for X-rays, NIH outsourced the data of 100,000 patients. So like that, there are medical archives which you can directly go and search. Especially for cancer, there is a cancer archive where you can get all the cancer images for different data sets.
Okay, sir. Thank you so much. Ma'am, do we have the virtual memento ready?
Yeah, sorry.
Meanwhile, can I request all the panelists to turn on the camera so that we can take a photo? Can't do it in person, at least here virtually. Yeah, so this is the virtual memento we wanted to present to you. Thank you for the insightful talk, and my apologies for earlier. I'd like to tell the audience that Mr. Kalkuleti, at such a young age, has co-authored 16 international publications, one book chapter, and has filed 12 patents. I'm sure that your talk on machine learning for breast cancer diagnostics has given you ways to proceed. For the early stage researchers present here with you, talking in detail about each stage of the analysis. Thank you for accepting our invite, sir.
Thank you, Sadia. Thank you, Dr. Padma, for giving this opportunity.
Thank you very much, sir, for spending your valuable time. So really, it's a great learning for all of us. Now, latest, actually, as per your statistics, many women are suffering from breast cancer. So early diagnosis is very important. So this is our topic for all the participants. I request all of you, please be aware of all these things. So maybe why I am attending this session, don't be think like that. Some of you may have sisters and mother and somebody neighbor to you. Please educate them the importance of early diagnosis of any cancer. Anything, if you diagnose early, so it is easily curable. Okay, by the time we are many people they are going for hospital, that is going to advanced stage. In that stage, it is not possible to cure. Okay, sir, your session actually thrown lot of light on how to take care of breast cancer, all those things. It's wonderful, sir. Thank you, Shivateja, for spending your valuable time. Thank you. I want to
Thank you
see
very
you
much.
in our campus very soon. COVID
Thank you.
will go away quickly, so that we are missing all of you. Actually, we planned this event, physical event. So I have postponed this event thrice, but even then we are unable to conduct physical event. So finally, we are able to conduct only virtual. I wish I want to see all the resource persons are a very eminent speakers for this 4-day SPS event. I want to see all of you in our campus. Thank you, sir. Thank you.
Thank you very much.
Our next talk, that is on ethics for healthcare applications by Dr. Chakravartula Kiran, will be starting at 11:45 a.m. I request the audience to stay connected.
Five minutes break. Sadia, inform break.
Yes, ma'am. So you can take a break of 5 to 10 minutes and stay connected. Please don't leave, because this is going to be an interesting session as well. Something different from what we have been listening for the past 3 days, that is on the technical front. Ma'am, you are sharing your screen. Can you please stop sharing the screen?
Okay, actually, I want to. I want.
Ma'am, you went on mute.
Is it okay?
Yes, ma'am. Ma'am, also after the break, if you can tell the audience about the demonstration, live demonstration of projects that we are having in the evening, it would be great.